right? But then I forgot to bring them today. So if you absolutely want to see your exam, follow me after class down in my office and I'll hand it to you, right? I just forgot them on my desk. I apologize. Now, in terms of the results, where is everybody? Where everybody is. Here are the results of the exam. So there was not a bonus. There was not a bonus on the exam, but the last problem I counted as a bonus. So I believe only 1 or 2 people got it. You'll be able to tell. But so the highest grade was a 102.5. So we had 1, 2, 3, 4 A's, almost an A. 1, 2, 3 B's, 1 C, 2 D's, 1 not passing, right? So that's the distribution of the grades in the class, just to kind of give you an idea. The class average was an 81, almost 82, and a standard deviation of 14 points. So overall, you know, I thought it was, it's not a bad average for that test, so I thought it went okay. I know some of you were frustrated that you knew how to do them, but had some issues or time or whatever, but it's where we are. So your grades online should be pretty accurate now. I had to send out a midterm report and midterm grades today. So you might see something in email that says, hey, this is where you stand in the class, something like that. But okay, any questions over this? Like I said, follow me after class if you want, and we will. I'll hand you that exam. All right, now we are going to continue with Lagrange, one example, and we're moving on. And this Lagrange will show up on exam 2, the final exam, right? You'll see Lagrange again. So here we go. We've got the whole idea behind Lagrange, because I know it's been an entire test, right? You took a test, and who knows how much you forgot about this, but with Lagrange, what we have is the ability to find the maximum or minimum value of a function if we have some sort of constraint to it. And so this problem is asking us to find the point or points on a sphere that are closest and farthest away from the point 3, 1, negative 1. So I want us to start by just thinking about the geometry in this problem. We are sitting here in 3-dimensional space. We have some point here that's given to us, 3, 1, negative 1. And we're trying to find a point, or the points on some sphere, right? That sphere is actually centered at the origin, isn't it? So we've got this sphere here at the origin, and that sphere has a radius of 2, right? A radius of 2. And we're trying to find the points on the sphere that are closest to that point and furthest away. So can you all see it? If you were to imagine taking from this point a line that would go through and punch through the sphere, right? If I just go right here, maybe I punch through here and here, right? Is this point the closest to that? I don't know, maybe not. Is that one the one that's furthest away? Maybe not. So I've got to figure out what points are closest and furthest away. I think this picture, maybe somewhere around there, y'all think those look right? It's hard, we're on a flat sheet of paper, right? Yeah. So, but do you understand the geometry of what we're doing? Okay, so all we know how to do is take some function, find its max and min if we're given some constraint, right? So the way you formulate this is the challenging part. How do you come up with the function that you're going to optimize, to maximize or minimize? Well, what are we trying to find the furthest or maximum and minimum of? Some distance, right? A distance. So let's just say like from here to just some arbitrary point on that sphere, right? That right there, let's call that D, right? Now, that's just the distance between 2 points, right? And we want to find when that's the smallest and when that's the biggest. So that's the thing we're trying to maximize and minimize. So what is the distance between this point and that point. Well, we don't know what that point is, do we? It's arbitrary. So I'm going to label this point right now x, y, z. Now, look, I do realize that it lives on the sphere, right? I realize it lives on the sphere, but that's my constraint. This equation right here is the constraint equation. It's like, okay, what's the distance between this point and this point? However, this point must be constrained to this sphere. So my d, my distance, well, we need to know the distance formula, the distance between 2 points, and that's from, I think, the first day of class maybe. Might be second day. The distance is the square root of, and it was like x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. In this case, I'm going to write x minus 3 squared. That's this x-coordinate minus this x-coordinate, plus the y minus 1 squared, plus the z, what, plus 1? Squared. Do you all agree that that's the distance between that point x, y, z and 3, 1, negative 1, right? And we want to know when this gets the biggest it can be and the smallest it can be, but we've got to constrain it, right? So the constraint equation is that x squared plus y squared plus z squared must equal 4. And so this right here is that g of x, y, z equals k when we were talking about Lagrange. This is the constraint equation. And then this is kind of like our, well, not kind of, this is our f of x, y, z, right? But I'm gonna suggest we do something. And this probably, I don't know if you'll remember this, this actually came up in Cal 1 if you did optimization problems, that if you're ever trying to maximize or minimize a distance, it's always going to involve a square root. So what we do, does anyone remember, or remember seeing it in Cal 1? Because the square roots suck because we have to differentiate them, right? Yeah. Okay, so instead of maximizing and minimizing the distance, we're going to maximize and minimize the square of the distance. Because let's say that this is our maximum distance, right? That if I square it, that's bigger than any other distance would have been squared. Does that make sense to you? Like, let's say that from here to here is the maximum distance. If I square that, that's going to be bigger than the distance from here to here or here to here, any other distance. It's a way that we can just kind of get around having to do the square root. Okay? So instead of doing this, we're going to try and find the x, y, and z that maximize and minimize d squared instead of just d. Right? So what's d squared? Well, d squared is that expression without the square roots, or without the square root, which I would rather work with this, right? I would rather work with this. And this is the thing I'm going to call my f of x, y, z. I think I'm going to write it over here. So here's what we got. We've got this. This is going to be our function of 3 variables. F of x, y, z is going to be x minus 3 squared plus, you don't have to do this step of squaring it. It's not necessary, but man, it makes the algebra and stuff much better. Yes?
It's still supposed to have the square on the...
What, am I supposed to do what? D squared.
D squared equals, or is it just D? To get rid of the square root?
I'm squaring both sides here. So I square that, and I square, and the square root goes away.
Oh.
I'm not sure what you're...
No, I see.
You sure?
Yeah, I got it.
That looks like just...
I got
Are you being agreeable? No? You're all right?
Yeah, I got it.
Okay. So instead of find the maximum of d, we're going to find the maximum of d squared just to make our lives better when we have to differentiate. But that d squared, that's what I'm going to call my f of x, y, z. All right? And now this is still our constraint over here. So Lagrange says, I'm going to erase. Lagrange says that if you want to try and find the maximum or minimum value of a function of 3 variables subject to a constraint equation, that you're going to have to set up how many equations? 4. It's going to be partial of f with respect to x equals lambda times partial of g with respect to x. Then partial of f with respect to y equals lambda times partial of g with respect to y. And then partial of f with respect to z equals lambda times partial of, it's all in the notes, right? I can scroll up and you'll see the formula. Right there, right there. That's it right there. Those 4 equations we have to set up. So let's go ahead and set them up. First equation, equation 1. I'm taking, do I need to write it down or can I just go right to?
Just go right to it.
You sure?
Yeah.
Okay. So what is the partial of this with respect to x?
2x minus.
2 times, I'll just leave it in parentheses, 2 times x minus 3, right? All that happens, 2 comes down, and then derivative of what's in there is just 1. So that's you could also distribute it to 2. That must equal lambda times partial of that with respect to x. 2x. Okay, that's our first equation. Equation 2. Okay, partial of this with respect to y. 2 times y minus 1. The quantity, the quantity y, shut up. 2 times the quantity y minus 1 equals lambda times 2y, right? And then third equation is going to be, this is all very similar, right? 2 times z plus 1, that quantity equals lambda times 2z. And then my fourth equation is actually this right here. I'll just put equation 4 over here. Is that all right? Okay, so now I need to figure out the x, the y, the z, the lambda that make all of these true all at the same time. So the first thing I'm seeing, I think it's in all of them, I can get rid of the 2's in all of them. I can divide both sides of these equations on all of them by 2. And if I do, I get x minus 3 equals just lambda x. And then here I can say y minus 1 equals lambda y. And here I can say z plus 1 equals lambda z. Okay. Man, I'm really tempted. Yes?
I have a question.
Yes?
This may be, that's a good question. If we only had the...
They say there's no stupid questions. I've been teaching for a long time. I disagree.
Imagine
No, I'm kidding.
that we didn't have we couldn't cancel out the 2's on the y and the z part. Could we still reduce it?
Say we couldn't do what?
If we couldn't reduce 2 by equation 2 and 3, could we still continue with reducing the equation 1?
Sure. Like just divide, yeah, because this is like its own thing, right? So you can divide both sides by 2, even if you can't do it over there.
Okay.
Yeah. The only time we have to worry is if we start blending them together, right? And then you can only set them equal if somehow, like if this is, let's say this equals 0 and that equals 0, you can set them equal to each other.
I remember you mentioning like there's certain conditions where you had to subtract to get.
Oh, yeah, no, right, like you wouldn't, I can divide by 2 because 2 is not ever 0, right? But you do have to be careful, you can't like divide by x.
Okay.
And that goes for any one of these. You can't divide by a variable. Well, you can, but you have to tell me, you have to say x can't be 0. Now I'm going to divide by x.
Okay.
So the recommendation is to move everything to one side and factor instead.
Gotcha.
All right, well, any feelings as to which way to go from here?
Suppose x is 0, y is 0, z is 0, and solve for lambda.
Well,
Can x be 0?
none of them could be 0 because then you'd multiply lambda by 0.
Yeah. Look what happens. If you let x be 0, that's 0. That's 0, right? And then you just get negative 3 equals 0.
I mean, suppose x.
No, this is good, though. This is good. Okay, this is good. Can we rule out right now x can't be 0?
Yeah.
Y can't be 0 for the same reason. If y is 0, then this doesn't make sense. And z can't be 0. All right? So I think maybe the first thing we should suppose is that x, y, and z are all not 0, right? Yes? So suppose x, y, and z are not 0. Now, when I write that, I hope we can all agree what I mean by that. I'm saying x is not 0, y is not 0, z is not 0. That's just a very short way of writing it. I could have written 3 different things. All right, so suppose they're all not 0. Now, okay, solve for what? Did you say solve for? Solve for lambda. See, now you can solve for lambda. Now can I divide by x? Can I divide by y? I can divide by z, can't I? So I can set them, I can solve all of them. Now there's nothing saying that I have to do this, but it just seems like maybe that's the way I want to go. Equation 1 becomes x minus 3 over x equals lambda, right? Pardon? Right, just dividing by x, we get that. And then what does equation 2 tell us? What do we get from equation 2? Y minus 1 over y equals lambda. And then the third equation, I'll squeeze it in right here, says that z plus 1 over z must be lambda. But that means I can set any of these equal to each other, can't I? Right, so let me do that. So let me set equation 1 equal to equation 2, and let's see what we get. X over 3, or x minus, I can't talk today. X minus 3 over x must equal y minus 1 over y. And now you could do, like, I guess, like we call it cross multiplication, right? We can do that now? Yes? So we would get xy minus 3y equals xy minus x. You all understand?
Yes, sir.
Yes? Let me keep going with that. Do y'all see we have xy on both sides? I can subtract it on both sides, it goes away. And all I get here is negative 3y equals x. That's good. I have a nice relationship between x and y, right? And
Wouldn't it be negative?
negative, yeah, sorry. Thank you for catching that. How about we just get rid of the negatives completely? Negative 3y equals negative x, and then that means 3y equals x. But I have a nice relationship between x and y, which means when I'm looking at my equation 4, I could get this in terms, I get this x in terms of y, I can get this y in terms of x, and then I'm down to like 2 variables here, right? But we've got another set of equations we can do this with. So if I set equation, what do you want to do? 1 and 3, you want to go 2 and 3? 2 and 3. Equation 2 equals equation 3 because the lambdas are equal to each other. So y minus 1 over y must equal z plus 1 over z. Do that little cross multiply again. We get yz minus z equals yz plus y. I think that same thing happens, doesn't it? But this time it's not, they're not both positive. You get negative z equals y. Yeah? So now you have a relationship between y and z. I say we go to equation 4 now. Okay? So let's see. Equation 4 now becomes, let's say we replace the x with 3y. What do you say? Yep. So this will be 3y, but it still needs to be squared. Plus, okay, y squared, I'm not replacing it with anything. It's y squared. And then z, what was z? We never solved exactly for z, but we could change that to a plus and that to a minus, right? So z is negative y. So I'm going to put here negative y. It's not going to matter because I'm doing what? Squaring it, and then equals 4. Look at that. I have a single equation, right? Single equation, one variable. Squaring things, 9y squared plus y squared plus another y squared must equal 4. 11y squared equals 4. Solve for y, divide by 11, y squared equals 4 over 11. And now square root, you're going to get 2 possible answers, plus or minus. Let me do the root of top and bottom separately, 2 over root 11. You could rationalize, but I'm just going to leave it just like this. Questions? Okay. Now I need to go somewhere with this still, right? But I just want to think real quick. Are we done? Like, we are supposing here at the very beginning that x, y, and z are not 0. And so we would need to also think about what if they were, right? But we already talked about that, right? Like, if any one of these is 0, it's over, right? If just x was 0, that first equation wouldn't be true. If just y was 0, that wouldn't be true. If just z was 0, that wouldn't be true, right? So my question, I guess what I'm trying to get is, have we covered everything? Like, does this cover everything? How do you feel? Is there anything we haven't looked at? Could 2 of these be 0? No, same thing. We cannot have any single one of them be 0, or we can't have 2 of them be 0, or we can't have all of them be 0. So does this seem like we've covered all the...
I think so.
Yeah, I mean, there's nothing else that we need to consider, which means these answers that we're getting here are going to be the answers. And we should have 2 of them, shouldn't we? 2 answers. One of them is going to be the closest, the other one's the furthest. All right, let's get the points. Let's see if we can figure out what these points are. So remember, I'm going to just get to the points. I'm going to figure out what x, y, and z are. I'm not going to put the lambda in here. Okay? So let's just figure out what we got here. Let's start with this positive one. So in the middle we have, let's go with 2 over root 11. Okay? 2 over root 11. If that's what y is, what's x? So come back here. 3 times that, right? Yeah. So if I multiply that times 3, I get 6 over root 11. And then what's z? Z is the opposite of y, the opposite sign. So it should be negative 2 over root 11. There we go. Now, that's the point, right? I don't know if that's going to be the max or min, but that's one of our critical points. Let's find the other one. It's just the opposite, isn't it? It's negative root 2 over 11. And then this one will be negative 6 over root 11. What am I doing? Sorry. I don't know why I just did that. Okay. So it's the negative 2 over root 11. And then the x is the same, and then the y is the opposite. There's our x, y, and z. Now, one of these points gives you the maximum value of that function. One of these points gives you the minimum value of that function, right? And this function measures the what? Careful. Measures the distance squared, right? What is the question asking? Find the points on the sphere that are closest and furthest, right? It's not saying find the distance, right? It's not saying that. But we do need to calculate which of these is the max and which is the min, right? So to do that, we can plug them in here, right? We can plug them in here. Let's start with, so now I'm going to check it. What happens if I take f and I plug in, I'm probably going to need a calculator for this because these are not nice numbers. Okay, if I plug that in, I have to do 6 over root 11 minus 3, right, squared. You understand? Mm-hmm. Plus dot, 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 dot. Can I just tell you what happens? Okay, I will tell you. And then the other one, we have to take f and plug in negative 6 over root 11, negative 2 over root 11, and then plug in 2 over root 11, and then do that, and we get some answer here. So let me tell you what happens here. The blue. So your answer here should be, this one will come out to be like 1.31, something like that, squared, and then this one will be 5.31 squared. In other words, this one's going to be bigger than that one. Okay? When you plug those numbers in, you're going to get a bigger number than this one. Can you just trust me on that? Which means that this point, what, is farthest away? And this one is closest. So yeah, you got to kind of take a step back and again appreciate what we're doing here. We've got a point in space, we've got a sphere, and what we've done is we've found the 2 points on that sphere that are closest and furthest away from that point in space. Now, there are some, Lagrange goes on, and you can have, instead of having a function of three variables in a single constraint, you could have two constraints. So something like, let's say we take that same point we just had, right? What was it, 3, 1, -1. And remember we had that sphere here? And we found the 2 points that were closest and furthest, right? Like let's say here, these are the 2 points we found, I'm just saying. That's when we did a single constraint. We were constrained to a sphere. But what if instead of just being constrained to a sphere, I also say you have to be constrained to this? I give you a second constraint. What is this equation? A plane. So imagine a plane coming through here and slicing through this sphere, right? Now, instead of trying to find the points closest and furthest away from that point on the sphere, you're only allowed to look on the what? Intersection of the plane and the sphere, which is going to be some sort of weird shape, right? Like this, like almost like a circle, right? Circle at an angle. So now, do you see that your answers are going to be different? Because you're not allowed to be everywhere on the sphere. You have to be at the intersection of those two. Okay? Yes?
Just real quick on the last
Yeah.
we were.
Uh-huh.
So we saw for those 2 points,
Yes.
for f of x, y, z is the d squared.
That's d squared.
So do we have to like square root that?
If you wanted to find the distance, the actual distance,
Oh, we're just looking for the point.
we just wanted the points. But if it was asking for the distance, we would have to take square root of those answers.
Gotcha.
Which is why when I showed you my answer, these are the right answers. These are the actual distances.
Oh.
I put those answers squared
Gotcha.
because to find those, you'd have to take square root.
Okay.
So
Yes?
is it, probably is, it's absolutely necessary that we plug it back in to the equation to prove that it's the maximum minimum. You couldn't just see that, well, x and y are both positive and z is negative, so it's in the same octant as.
Yeah, you could probably
Yeah.
deduce it from where the point is.
Yeah.
You could
If it's
probably
like a
deduce
sphere
that.
and you know that it
Yeah,
has to go
yeah.
that way.
As long as you feel comfortable, like you know where it is relative. Yeah, I think you could deduce it that way. Yeah. All right. So I'm telling you there's another, there's a Lagrange with two constraints. We are not going to do any of those problems. I'm not going to test you on any of those problems. But I do want to just at least show you one, like the setup of one, okay? So here are the notes that go with it, all right? And it's a little confusing, but you know how we just did 4 equations? With Lagrange, with 2 constraints, you actually still have 4 equations, right? Sorry, you have 5 equations instead of 4. And what you do is, you see how this right here is the same thing we just did. It's partial of f with respect to x equals lambda partial g with respect to x. Then there it is again, the next one, then the next one, and then your constraint, right? But if you have a second constraint, here's your second constraint. If you have a second constraint, we call that h of x, y, z. What we do is when we do this, we have to add another variable, which we don't know. We call this lambda, that's mu, and then partial of h with respect to x. These two added together have to be equal to this, and then so on and so forth. So let me show you a setup on one. I have the example I want to set up. We're not going to go through all the work, okay? We're just going to set it up just so you can see it. So do you all see that we have this right here, function of 3 variables, right? Now that we can't see it, remember that function lives in 4-dimensional space, but we are constraining it to this and this, 2 constraints, right? 2 constraints. So I went ahead before class and I graphed those 2 constraints. The red was the first constraint. The red was x, y equals 1. And then the other one was, I think it was y squared plus z squared equals 4, I think it was. Was it 4? It's right here. Hold on. No, equals 1. Equals 1. Equals 1. I didn't mean to make that spin like that, sorry. So you have the x, y equals 1 is the red, and then the y squared plus z squared equals 1 is that cylinder, right? And so where those two hit each other are the black curves, right? You see those? So what we're doing is we're saying, all right, if you were to take that function, where was the function? I erased it. All right, don't have it up here. F of x, y, z. The function that they gave us was, I think it was xy plus zy or something like that. So if you take this function, you want to know the biggest that's ever going to be and the smallest that's ever going to be. If you're only allowed to plug in points on this black curve, that's what we'd be doing here with this. Understand the difference between that and like the sphere problem? We have two constraints, which means that we don't have a surface we're looking on, we're actually looking on a curve. All right, so let's go ahead and set it up. Okay. So my first equation, equation 1, is going to be, I'm going to write it down, partial of f with respect to x equals lambda partial g with respect to x plus mu times partial of, h with respect to x. Okay, so that's obviously what f is. Let's say that this is our g function, and this right here is our h function. So g is a constant, h is a constant. Okay, partial of f with respect to x is y equals lambda partial of g with respect to x. Y plus mu times partial of h with respect to x. There's no x in here, right? So what? 0. Okay, that would be our first equation. All right, now equation 2. Partial of f with respect to y equals lambda partial g with respect to y plus mu partial h with respect to y. Okay, what is the partial of f with respect to y? X plus z or z plus x, right? Partial of that with respect to y is z plus partial of that with respect to y is x equals lambda. What's partial of g with respect to y? X plus mu times what's partial of h with respect to y? 2y. Okay? Second equation done. Third equation. Partial of f with respect to, I'm not going to write it up here. Well, I'll write it. Partial of f with respect to z equals lambda partial g with respect to z plus mu times partial h with respect to z. F with respect to z? Y equals lambda partial g with respect to z. 0 plus mu times partial h with respect to z. 2z. Okay, and now you have equation 4, which is this one. Equation 4 is that one, and equation 5 is this one. Got it? So we've got to find the x, the y, the z, the lambda, and the mu that make all 5 equations true at the same time. Now, I'm not going to go through this, but let's just see. It's not as bad as it looks. That goes away, right? And so this tells you that y equals